this series of short videos, we'll be exploring the essential concept of the mole. It's an essential concept as it allows us to relate the unseen world of atoms, molecules, and ions, electrons, to what can be measured in terms of mass and volume. Now, I ask you to keep an open mind as we explore this concept. I'm assuming that you've all had previous experience with the mole, but I think you'll see that we're taking a slightly different perspective here. For one, I want to present the fact that the mole is more than just a number. It is the SI unit for the amount of substance. So in spite of the fact that you see in bold and in a box 1 mole of elementary particles equals 6.022 times 10 to the 23 elementary particles, as I say, it is more than just a number. In the same way that the unit for mass is kilogram, the unit for volume is liter, the unit for time is second, the unit for the amount of substance is the mole. It has the symbol MOL. Now the mole used to be defined in connection to the number of particles in 12 grams of isotope carbon 12. It has more recently been defined as the amount of substance in exactly 6.022140076 times 10 to the 23 elementary entities. This number is the fixed numerical value of the Avogadro constant, which is symbolized as Na, and this is called the Avogadro number. So a little bit of background here. For one, Amedeo Avogadro did not come up with this number. Amedeo Avogadro was an Italian lawyer that eventually became a physicist who in the early 1800s proposed that an equal volume of different gases at the same temperature contains the same number of particles. He was going against conventional wisdom at the time and eventually led to the idea of having identical number of particles for a given volume of particular elements. It wasn't until the early 1900s that a French physicist, Jean-Baptiste Perrin, was the first to coin the term Avogadro's number. His work on Brownian motion allowed for an estimation of this number in 1909. Shortly after this, an American physicist, Robert A. Millikan, was the first to accurately determine Avogadro's number because he was able to measure the charge on a single electron to essentially 9 significant figures. The idea here is the charge on 1 mole of electrons was known to high accuracy and precision, like to 9 significant figures. The charge on the single electron was determined, and of course dividing the top number by the bottom number allows for the determination of the number of electrons in 1 mole. Since then, Avogadro's number has been determined by several other methods, and this is currently the accepted value presented here on the screen. In the picture on the left, you can see Robert A. Millikan as well as Albert Einstein, as they indeed worked together in relation to the photoelectric effect. A couple of other things to mention. Technically, when the concept of the mole is used, elementary particles should be specified, and these may be atoms, molecules, ions, electrons, photons. So in other words, we should be saying 0.23 moles of carbon atoms, 0.56 moles of nitrogen molecules, 0.49 moles of calcium ions. The thing is, it's rather tedious to always be specifying the atoms, molecules, and ions. You'll see that I'll be doing this at first, but gradually we'll wean ourselves off of this, and I expect in tests and things that you would just be saying something like 0.23 moles of carbon, 0.56 moles of nitrogen. Lastly, I'll mention that, of course, on the periodic table, when we see the numbers that are associated with the various elements, these numbers can be considered as the molar mass of the element. This number, of course, is equivalent numerically to the average atomic mass as well. So the two numbers are identical. In one case, it's associated with the average mass of a single atom in units of average atomic mass. In the other case, it's associated with the mass of a whole mole of that particular element in units of grams per mole.